Good evening, everyone. Good evening, all my viewers. Good evening, everyone, all my viewers. So, kindly write in the chat box, am I audible? Okay. So, hope I'm audible. Yes. Thank you, everyone. Hope you are doing good. So, as I've said in this particular lecture, we will clarifying the few things. One is a concept. We will highlight some important formulas, which is very much important when it comes to propulsion, and we will also discuss the tips and tricks, some of the tips and tricks that how you can remember those complicated formulas, because here we have so many problems, right? So many formulas we have, how you can figure it out. And there are certain things like what are the do's and don'ts, and some more, if you have some kind of doubts, we will clarify those things. Okay, so I will just compress all the things together. All right. And so side by side, I will expect some responses from your side. And as much as I can, I will try to do some practical, some types of numericals with you, or we'll discuss that how you can solve those things. Okay. So, without wasting much time, let's proceed to our first and foremost topic is our basics. So, before starting into the syllabus or telling like what are the concepts and how to prepare, and especially as you have only few more days left for your final exam, I mean final gate examination. So, I will tell you what are the areas you must not skip, and from where definitely you will get a question. Now, as this gate 2022 is concerned, we can expect out of 100, like again, 25 to 30% questions will be from this, right? We can expect it, but again, we cannot assure you properly. But if you see overall all the gate question paper, we will expect that it will come within this 25 to 30, and this is a proportion is one of the very much scoring among the all. It's very much scoring. So let's begin with the first topic. Okay, the basics. When we talk about thermodynamics, right? So when we look into this topic called thermodynamics, it's itself a lot many things are hidden. So first, you must understand the law of thermodynamics. What are the laws of thermodynamics? Okay, laws of thermodynamics. So if we talk the applications of zeroth law, we can ask about first law, and also talk about the second law and its application. So each of these laws signifies at its own place. Okay, so you cannot skip. This is one of the very important topic, laws of thermodynamics. Maybe you will get some few questions or some reasonable reason based question, but you cannot skip. This is one of the very 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 important. Now you may also expect from this laws of thermodynamics, like thermodynamic properties. Okay, thermodynamic properties. It's been of two types: extensive and intensive. extensive. So what are the examples of extensive and intensive property? So you have to study. So talking about how we can remember how these two properties are different with one another. They're different in the sense of mass. So extensive property we call as when it is dependent to mass. Okay, it is dependent. And intensive property is independent. Okay, independent to mass. Okay, so let's see some examples like volume, enthalpy, or entropy, internal energy. So all those things comes under the extensive property. Intensive is like pressure or something which you have a specific energy or have a specific enthalpy. So all those things comes under the intensive property. Now I personally prefer to, it's better to remember in terms of some tricky things to avoid certain things because there are huge things to remember. So if you remember some clue, so as it is I starts with the intensive, right? Another I is independent mass. Okay. So this I got some similarity within it. So if you remember this small tricks, I hope it was going to be easy for you to avoid this mistake. That how an intensive property and extensive property are connected with one another. Right? Now, moving further, so this is one area of asking questions. Now, next part is there may be of like thermodynamic processes. So, one or two questions every year we used to get from this topic is a thermodynamic processes. Okay, we used to get the questions on this thermodynamic processes. So basically, what is thermodynamic process? You cannot skip this point as well. It's there are a lot many different types of thermodynamic processes, right? So when we talk about this process and path, okay, we will discuss that also. What we call as a path, there are some series of states, okay, through which a system passes within the process. Like I can say there are multiple different types of process. I can say isothermal process, I can say isobaric process, isochronic process, right? Iso we have another process called um so a diabetic process, right? Now, if I combine more than two things, right, from one state to another state using certain process, that is called as a path. How? From one point to another point it is deforming. And what is the process behind it? If I say from 1 to 2, if I am shifting some particular fluid is changing its property from 1 to point 2, what is the process behind it? If from 2 to 3 it is shifting, what is the property behind it? If 3 to 1, if it is changing, what is the property behind it? And combiningly 1 to 2, 2 to 3, and 3 to 1 becomes a cycle. So there may be a questions, one or two questions from based on the path and the cycle. What do you understand by the path and which is the cycle? They may be asking. Now there is again a very unique connection. What happens with the cycle, right? So this is another very important thing to note down. The change in the value of any property of a cyclic process, any cyclic process, is obviously going to be zero. Uh, if you go through our 12 years question paper, out of that 12 years, every year or one and other years, you can find this question or the concept of this question. Okay, so they ask for 1 or 2 marks from this particular topic, cycle. Okay, change in the value of any property of cyclic process is will be zero. That means if I consider the pressure, if I combine all together, it has to be zero. If I consider the within the cycle of the specific volume, it has to be zero. The temperature, it has to be zero. That means whatever any property of a cyclic process, it has to be zero. This is one of the important topic. Two voices are coming. Okay, is it fine right now? Sorry, just now I have seen it. Is it fine right now? Hope it is fine. All right. Okay. Without wasting time, let me move forward. All right. Now this is one of the point. Now, without skipping this process. So this is the basic of all. So thermal, isobaric, isochronic, adiabatic. Okay, this is the base of all. So we will again come to this process, how combinations of these processes and we can develop something. So isothermal is like obviously by the name we can define it. It's a we have a constant temperature. Isobaric means it's a constant pressure. Isochronic means constant volume. And here we have adiabatic, that means a constant have zero heat transfer. So coming back to this one, like they might ask you some example. Like let's take an example of Brighton. So we will come to that Brighton cycle also in the upcoming, because which works for an jet engine. So for a Brighton cycle, we'll see they will give you some. For an example, they will give you a compressor. Okay, so they will ask which process does it work, or which is the appropriate process for this combustion or compressor zone. So likewise, they will ask you, right? So we will come to that questions in the later part also. So first, let me finish off this basic thing, the thermodynamics. Now talking about this basic process, path and cycle, there are one more important thing to remember and understand. One is a path function, another is a point function. Okay, so there may be a questions from path function and point function. So path function means, for an example, right, you have some graph with respect to some specific volume with your pressure, right? We have 2 points. We have 2 points. So let's consider one is moving from 1 to 2 in a straight line. In a straight line. This way. That is A. This path is A. Another, but the final state becomes same. Another one is moving to the another process or another state from 1 to 2. Same state. Their final destination is, initial and final destination is same, but the process are different. Let's consider B. There is another process or the path they following C. All right. Now, if I see the change in, so if I see here, if I take P1, here I have to take P2. If this one corresponding value is V1, this is V2. The final destination is same, right? So the area under this curvature represents different work done, because if I have to find the work done, I have to find out the area under this. So work dones are different, right? So it is not the function of a end process. It's a, it depends on which path I'm following. It depends on what is the which path, whether I'm following this A path, whether I'm following the C path, whether I'm following the B path. Our work done is going to be differ. So that's why we always call either it is a heat transfer or the work transfer. It is defined as a path function. It is defined as a path function. It is not depending on the final state. It depends on which path or the which process I'm following, right? But the same, if I have to see for an like when we call as a point function, when it is independent of the path, it is only focus on the final destination and the initial destination. So let's take an example that the path one or the state one is an initial stage, and state two is our final stage, right? So it is not depending on the path which is following. So that is known as a path function, which is moreover as an internal energy, which is moreover an example of an internal energy, right? Okay, moving further. Okay, I hope I have making this things clear, because there may be a possibility of asking question from path function and point functions. This is one of the important topic. Now we will also discuss some of the important another important point to take away about the heat and work done sign convention. This is another very important topic where most of the student I've seen get confused, right? There is a simple way to remember this thing, right? I will just going to share a very simple tricks. So just remember this diagram alone. So all those positive negative will get confused. Just consider there is a system, right? Right. So there is with a heat transfer and work transfer, there is a some positive negative relation. So remember this color graph. So when the heat entered, so remember this heat transfer to the system, right? Heat enter to the system is always positive. When the heat is entering into the system is always positive. And when the work done by the system is again considered as a positive one. But whereas when the heat leaves out or heat transfers from the system, we can say either of it from the system, it is always going to be negative. And when the work done into the system or on the system, something relevant to it, when the work done on the system, it will be negative. Okay? It is going to be negative. For a good example, like all of you know, there are basic parts of a jet engine. So if I have to say work done by the system is an example of turbine, and work done on the system is a compressor. Okay, and where the heat is done into the system, where heat is added, moreover heat transfer to the system is when the heat is added into the system. So it is an example of a combustion chamber. Okay, and when it is leave out from the, it's a very simple heat exchanger. I hope I made you clear, all of you. These things, these are the simple basic things you always keep in mind. And in future, whatever the other things you are going to see, all are relevant to this only. You are not going to keep them apart from this basic concept. When you see for heat engine, heat cycle, and other things, this is the part of that. You cannot shift. So this is the principle we are going to implement in the second law of thermodynamics and all. Right now, uh, what you have to do, what are the things you cannot skip. This is the PV diagram. Okay, PV diagram for different cases like isobaric system, isochronic system, okay, isothermal system. All those things you have to, for all those things you have to remember the graphical representation, how the PV graphs are going to work. So I'm just going to show you a simple graph which compiles all those things. So this is actually the general equation, work done 1 to 2. Okay, one more thing. If I write work done 1 to 2 is not equals to W2 minus W1. What does that mean? From one state to another state when I'm shifting, right? We cannot write the work done like this. That means the work is in the process from 1 to 2. Does not mean that is equal to W2 minus W1. We cannot write this. Okay, sometimes in gate they also ask whether it is equal to or not equal to. It's not equal to. And if they ask the reason for it, the reason is because it's a path function. It's a path function. What I said, the work done, it depends on which path or the which process it will be moving from one state to another state. But whereas if I have to write about the internal energy, if it defines by U, if 1 to 2, I can say it is equals to u2 minus u1. Why? Because it is a point function. It is irrespective of which is the what path it has followed. It just depends on the state, final state. Okay, so this kind of questions might come, right? So maybe for 1 marks or 2 marks. So be careful with this concept. Okay, the path function and the point function. Now coming back to here, this is a general equation which is P1 V1 minus P2 V2 by n minus 1. So which can also be, so there may be some numericals relevant to this particular formula. So if it is new to you, you can note it down, n minus 1 by n. Okay, this n minus 1. N minus 1. Okay, n minus 1. All right. So just consider this is a point 1 and this is a point 2, right? So remember this graph. So this is a basic formula. Here this is n equals to 0 and this is n equals to infinity. And as it is infinity, here it is going to be n equals to 1, n equals to 2, n equals to 3, right? For different types of n number, different types of n equals to 0, this is going to be the formula, right? Now just see when the n is 0, right? Just take this example. If you take n equals to 0, right, what will be the value of your this work done? What will be the value of your work done? Obviously it is going to be 0, right? So work done is going to be 0. Work done is going to be 0 for an isochronic process, right? Work done is going to 0 in an isochronic process. In isothermal process, if you substitute, so it is going to be n equals to 1 when it is an isothermal process. n equals to 0 when we have a constant pressure. When we have a constant pressure, if you substitute here n equals to 0, whatever the equation you will get, it will be for a constant pressure. So if n equals to, if you substitute 1, you will get that one for your the value for the isothermal process, right? And n equals to infinity is for the constant volume process. Okay, just remember this basic things and remember this graph. And if they ask whose work done is the highest, okay, if they ask you in a graphical representation that whose work done or expansions is going to be more as compared with the others, so it's going to be isobaric expansion. So mostly in propulsion, this kind of this type of things are quite expected. Like whose work done is going to be the highest sequentially, right? Thermal, then adiabatic, adiabatic when n value is 1.4. Okay, adiabatic, and then isobaric. This is the sequence. So do remember the sequence of the work done process. Okay. Now, then first law we have discussed, and yes, definitely you will get the application of first law of thermodynamics. Definitely you will get one question, definitely, and it is from steady flow energy equation. So if you revise this all the 12 last 12 years question paper, you will get at least one question of 2 marks from this topic, definitely. And that also either NAT type or the MCQ type. Okay, NAT means that numerical aptitude test one, which is having no negative marking. You have to fill according to the decimal place. So they have some basic standard formula. So I will just write down the formula over here. So H1 plus V1 square by 2 plus Z1G into dq by dm, okay, equals to H2 V2 square by 2 plus Z2G and d by dm. Definitely you will get a question. Now this is a general equation, right? You have to remember this equation. Now what is the point? Like you can use this formula if the units, the enthalpy units or work done unit all are in of joule per kg. Then use this formula. If there is in joule per kg, use this formula. If it is in kilojoule per kg, then obviously you have to change the unit. If it is in kilojoule per kg, what is the difference you have to make? Just divide this, change here into 1000. Okay, here with 1000. Here will be around 2000, be 1000. This is a simple change. If it is in kilojoule per kg, you have to be very much careful with the units, right? Repeatedly I'm telling you guys, you have to be very much careful with the units. Now moving to the next, uh, further another, we can rearrange this formula also. How we can rearrange this formula? We can also write like that: m dot 1 h1 v1 square by 2 plus z1g plus dq by dt equals to m dot 2 h2 plus v2 square by 2 plus z2g plus work done, right? So this is the you might need to implement this formula. So this is again when you are implementing joule per kg. Once you if the given values are in kilojoule per kg, just like this, you have to make the necessary changes according to the given one, right? Now there are certain basic conditions, terms and conditions to apply on this further equation. For an example, if they give that it is you have the throttle device, okay, and considering the enthalpy on both the throttle device are same, so what you have to do, h1 equals to h2 on that condition if it is a throttle device. If they said it's a turbine and compressors, so accordingly you have to make the necessary changes, turbines and compressor. If it is a nozzle and diffuser, so we have to remember in the nozzle and diffuser, there is no heat transfer and no work done. So in that cases it is going to be zero. It is going to be zero. They can also ask or reframe the question like what are the following terms will be zero, whether there will be heat added or heat will transfer will be there or work done will be there in nozzle and diffuser. So you have to be careful. The nozzle and diffuser, there is no heat added or no heat work done by the system. But whereas same like a turbine and compressor, so what you have to do, there will be existence of work done, but no heat added, no heat added. So this is either for whether it will be positive or negative, it based on what type of power in power output or input. So it will work on the system or work done by the system. So accordingly, the plus and minus symbol will be considered. So here this is for the turbine and compressor. Fine. Uh, uh let one one is not, just a second. One is not coming zero. Um, one is for isothermal. Okay, it will not come zero. One is for isothermal. For in isothermal formula, you will get mm, W12 will become P1 V1 ln V2 V1. Okay, you will get this equation. We'll get this equation. Okay, now moving to some important tips where you can also get some problems. First is for closed system. Okay, for closed system. So for closed system, there is some conditions. The summation of all the heat added is also going to be the same as summation of all the work done, right? For an example, they will give you one system. So Q1, Q2, Q3, W1, W2, W3. Among this, all the values are given, provided to you, and they will ask you find the value of W3. So what you have to do? You have to do Q1 plus Q2 plus Q3 equals to W1 plus W2 plus W3. W3. So all these values are known. This known. Keep this thing other end. You will find what is the value of W3. Right? Some simple formulas might come from this. Okay. Now there is another way. They might give you some graphical like V and P. Okay, like kind of let's assume um, like this. The graph is going like this. Okay, and they will give you all the parameters. What is this parameter? All those parameter will be given, right? All those whether it's 100, this is 200, this is point 0.3, this is point 0.7, and you have to find the work done on this particular process. So what you have to do? Simply the area under the curve, you will get the work done. So you can find the area of this region, right? Simple maths. If you can create a block of this entire thing, find the area, and that is going to be the answer. Sometimes they might ask you on this as well. Okay. Now one more tricks relevant to first law of thermodynamics. Some more important notes. Okay, a simple tricks to remember. As you know, first law of thermodynamics, like dq minus dw equals to du, right? So you implementing this, so it have some outputs, following outputs at constant pressure. Okay, at constant pressure, change in internal energy is equals to heat transfer. Okay, so keep this. This is one of the important point to take away, right? This is one of the important points. Sometimes they ask in one mark question, like if it is in constant pressure, what is going to happen with the internal energy, change in internal energy with the heat transfer? They are going to be equal. The change, there is some derivations, right? So here nobody is going to ask you to or they will ask you to derive some derivation. So this is another important point to take away, right? Now next we have, this is the first law. Now moving entering into the second law of thermodynamics. Okay, so this is another very important, where you have to know heat engine, right? So rest of our syllabus is fully relevant to heat engine, right? The efficiency of the heat engine, how it works. Then we have some refrigerator, heat pump. What is the working process? Very importantly, they have one factor. So first, I will start with the heat engine. We have heat engine. We have refrigerator, refri. Okay, and another we have a heat pump. Okay, so these are again a very important topic. They ask mostly numericals. So do remember. So obviously, in a heat engine, they will ask thermal efficiency. There is a possible to ask a question on thermal efficiency. So this is a common for any efficiency. Any efficiency. What is that? Net work output to the heat input. So work output to the heat input, right? Try to remember with a short notation, so that will be easy for you to remember it. Now how we get net output? Obviously the subtraction from the turbine, work done from the turbine to the compressor, we get the net output. And what is the input? Where we are adding the heat. So the combination of this is nothing but the q1 minus q2 as well. So we can write 1 minus of q2 by q1. So either we can implement this equation or this equation. Okay, there may be some short numericals. right? Now there may be another question like work ratio. So work ratio is again net work output to the output, that means turbine, right? So there is again, we have to substitute wt minus wc and we'll get this. Then we'll move to refrigerator. Refrigerator, we both here we use one common terms, that is called as a coefficient of performance. In short, we call it COP, right? This refrigerator and heat pump has a unique relation. So what is that COP refers? It refers the desired effect to the work input. Okay. Now what is the purpose of this refrigerator? Refrigerator, obviously it maintains the temperature lower than the outside temperature, obviously to cool down something. And obviously heat pump is to maintain the temperature above the surrounding, to warm up something, right? So what is a desire then in the refrigerator? Something cooling. Cooling is desiring. So where we have the cooling temperature, we are going to add that. We basically take the temperature 2 as a cooling one, and work input, that means sorry, q q2. Q2 is a cooling one we consider, and work input is the W net, which is nothing but Q2 by WT minus WC. Whereas desire is we need a warm up, that is the heating effect. So COP for a heat pump is a Q1 where we add heat, Q1 WT minus WC. And if I combine, they have the relation between refrigerator and heat pump. You must remember that COP of heat pump is equals to COP of refrigerator plus 1. This is again an important formula. This is again an important formula. Very, very, very important formula. Right? Now we have almost covered our basic thermodynamics, which they mostly ask. You cannot skip these things, like small things. Another touch up of this second law of thermodynamics, definitely you can expect that some relevant questions is a Clausius theorem. Clausius theorem. You just need to understand this expression. You just need to remember that is what is entropy and what is a property of entropy. So already we have discussed this entropy thing and the cyclic nature. I think I've highlighted and wrote something. Race, the change in the value of any property of a cyclic process. So as I've said, it is whatever, it's a entropy or it is a change in temperature, it has to be zero, right? It has to be zero, and that is the relation with the Clausius law, whether it's a reversible, irreversible conditions. So you have to remember that. And how this entropy varies with different process. So if I talk about whether it's a isentropic process, if it is an isentropic process, whether it's an isothermal process, how it behaves, so that also one of the important, do not skip this point, especially because this when you see the other topics also, which is going to be interconnected. Okay, so don't leave these topics whatever I have discussed. Apart from that, there are some basic thermodynamic equations. You must remember it before going for an gate exam, because you never know when you need to understand. As I have said, here we will also discuss the formulas. So you might think that this is nothing important or so. but you do need to understand this simple basic thermodynamic equations. You must know it. So please, I'm writing it. If you feel you know and you're confident enough, it's fine. Otherwise, you just take it down. Okay. So T, I know. I hope you understand what it T defines. TDS equals to DH. Represents enthalpy minus V dP. Okay. Now another way we can write this H equals to U plus PV. This also we can write this. Now another one is change in entropy. S2 minus S1 equals to Cp ln T2 by T1 minus R ln T2 by P1. You might expect this some numericals using this formula itself, maybe 1 mark or 2 mark, and you should know how this Cp and Cr is related with one another. So there is a simple way to remember. One is Cp by Cv equals to gamma, another is Cp minus Cv equals to R, right? So I have seen many of the students get confused with which one will come first, whether Cv or Cp. So remember in an alphabetic way. So P come first, then comes V. So Cp by Cv equals to gamma. Here also it happens the same. Cp minus Cv equals to R, right? And if you know in this two itself, either of the value of Cp, you can derive it by yourself. And maybe sometimes they will be giving you some constant term like what is the value of CPA. So if not, do remember 1.005 kilojoule per kg Kelvin. These are some constant value. It will be helpful for you if you remember it. And Cp G in for a gaseous 1.147 kilojoule per kg Kelvin. Okay. So this is for the compression and this is for the expansion one, right? These are the two values. It is better to remember it. So I think we have somewhat given the layouts, the important facts, which you can expect for sure. Expect for sure, I'm telling you, especially from this topic. Now moving for the boundary layer, heat transfer and combustion and thermochemistry. So let me first go and give you some idea behind this thermochemistry. Thermochemistry and this particular topic which you are seeing right now, especially heat transfer and combustion thermochemistry. For combustion, definitely one question will be there, like using efficiency. 100%. Using efficiency, will get one question. But talking about the thermochemistry, it's like rarest of rarest question, but one of the very easy and scoring part. Okay. So first, in the coming to the point of thermochemistry first, right? So what you have to do and what are the things you have to remember? Thermochemistry, right? First, it's a very small topic, right? Just go through some basics, understanding what is a stoichiometric meaning, what is the meaning of stoichiometric, what is your stoichiometric ratio. There is some relation with the stoichiometric and equivalence ratio. All right. So some textbook they refer the stoichiometric as lambda and equivalence as pi. Okay. Now what is the actual relation between it? Stoichiometric refers that air to fuel ratio of actual to air to fuel ratio of an ideal, which is we actually call as a stoichiometric. Okay. Which actually we call in a form of stoichio. And what is equivalence? Right? Equivalence is the fuel to air of actual by to fuel to air of stoichio. Right? Now, what will happen, how the relations, like it is all about the thermochemistry, means how the combustion process, what's the amount of mixture of fuel and air, it's all speaks about that. So if we have lambda is less than 1, okay, lambda is less than 1, what will happen here? So basically, sorry, so what will happen if lambda is less than 1? So that means if I'm putting here less than 1, right? So which one is becoming greater? AF by, that means the ideality is more and the mixture ratio is less as compared with the ideal one. So if the I mean this actual one is less and with compare with the ideal one, so obviously it will not, fuel is more and the air is less, right? Basically we can say here is fuel is more as compared with the air in this concept. So if the fuel is more and the air is less, so it will not lead to an combustion. It will finally lead to an incomplete combustion, right? Incomplete combustion, right? And if it happens vice versa, if it is greater than 1, so obviously if it is greater than 1 means the air is more as compared with the fuel, air is more as compared with the fuel. So there we can state them as excess air. So either of that, it is not been a ideal solution. So when we say stoichiometric, when this lambda is equals to 1, right? When the lambda is equals to 1. And how we will know this is the right mixture? How we will know this is a right mixture, right? So to find out or identify whether the flow is a right mixture, there is some formulations to find fuel to air stoichiometric. And what is that? Number of air molecules into molecular weight of air by the number of fuel molecules into the molecular weight of fuel. As simple as that, you have to make use of this basic equation. First they will give you what are the combustions they are mixing it, first balance them, then put in this equation to obtain it. All right, this is a very simple and rarely they ask this question, very rarely they ask this question. So I can give you one example, like mm, okay, let me take this 3 C3H8 plus O2. So obviously what will be its product? CO2 plus H2O is going to be the product. Now whether this equation is balanced, obviously no, because here we have 3 carbon, here we have 1, right? So we need to balance it. If I have to balance, then let me put 3 here, 2 6. So here we need 1 7, sorry, not 7, here we need, it's coming at odd number, H2. So 2 is also need to be there. So we have to put as 4, 4 plus 6, 10. So I can keep it 5, right? I hope now it's balanced, right? So that means to burn 1 mole of your C3H8, okay, I need to, which produced 3 mole of carbon dioxide, 3 mole of carbon dioxide, right? Or make a complete combustion, it took 5 mole of oxygen. I can state in different ways. Now what I'm going to do this, my motto is to find out their air fuel ratio. So what is the molecules over here? So I'm going to put them together. So first we have either by air by fuel or fuel by air, either of that you can do. So this is your fuel and this is your air. Okay, so here you have first 4 moles. So 4 moles into 2 into 16, right? Into 16 plus how many moles you have? You have 1, right? So carbon is you have around 3 into 12 plus 8 into 1 you're gonna do. So whatever the value you're getting, this is going to be your stoichiometric value. All right. So this is how you have to find out the value of your stoichiometric. There may be 1 mark or 2 mark. You can find this kind of questions are there on your gate exam. Okay. Now, mm, till now, any questions? Anyone want to ask any question? Okay. Let me give, or else you can jot it down. We will ask in the end. Okay, fine. Now we will move to our next topic is like boundary layer. So which already I have covered a part of it in aerodynamics. So let me give you a glimpse what you have to do in this boundary layer. So first of all, how this boundary layer occurs, what are the forces acting on it, then how this boundary layer is different with your laminar boundary layer is different with your thermal boundary layer. At what condition? How will you find the flow is attached? How will you find the flow is detached? Okay, all those things are important over here, right? Now let's move to our core part of our thermodynamics and the propulsion. Okay, core part. So which comes here, our definitely and do not skip the problems on the engine performance and the thrust efficiencies. Never skip. Definitely one problem will be there. One problem, then coming to the this thing, do not skip a problem on centrifugal compressor or any type of compressor, axial compressor or centrifugal compressor or axial turbine. Definitely, you can take like 2 to 6, 10. You will easily obtain 10 marks from this particular topic using by only understanding the efficiency formula and other relevant things. Definitely they will be there, it will be there. And for turbine problems and compressor problems, you have to remember the your velocity triangle. So here what is the main thing, if you have a very short time, if you are if you want to within a short period of time, if you want to crack your gate, so you have to remember the velocity triangle, no other choice. You have to remember the velocity triangle, right? So here I will show you, so as there is a lack of time, I will just show you the efficiency formula, how you can easily remember your easily revise and remember the efficiency formula and the velocity triangle diagram for all these things. And then I will give you some glitch about this rocket propulsions and other how you can prepare, and what are the formulas and thing, all those things I'll be discussing. All right, now let's get started about the aerothermodynamics of aircraft engine. First and foremost, what you have to do is you have to remember our what we call as a TS diagram. You have to remember that. Whatever it takes, you have to remember your TS diagram. Okay, you have to remember. So TS and each and every process. So first and foremost, what are the basic processes we have? We have first we have a diffuser. What happens in the diffuser? The air enters into the diffuser, and so gradually the shape, here we are talking about a jet engine. So the what is about the shape? It is almost like a divergent shape. It is almost like a divergent shape. Why we have a divergent? Because we need to decelerate the speed and increase the gradually ramp the pressure. So gradually, so that means in the diffuser the pressure is going to build up. Now itself the pressure is going to build up. Then followed with this gradual pressure, it is moving to the compressor. So compressor, the end of the compressor, it is the extreme pressure. Then we have the maximum pressurized air is moved or enters into the combustion chamber. So where the fuel and air get mixed, all kind of chemistry things happen over there, and at the end, it leaves the out from the turbine blades and finally expels out to the nozzle, and that's how the velocity is created. As simple as that. Now here, what there are many sort of ways that question can come. One is what is a process? Okay, one is a process. So when we talk about the diffuser to compressor or whatever it is of an isentropic process. Okay, it is an isentropic process. Now, talking about combustion, what is the process? It is an isobaric process. And again, it is an isentropic process with an expanded isentropic process, a compression isentropic process. Right? Here we don't have this. Okay, don't have this. So, let's consider when it's entering, it is A, and leaves out from the diffuser is point 0.1. Now 1 to point 2 is the compressor, 2 to 3 is our combustion chamber, 3 to 4 is our turbine, and to 5 is our nozzle. Clear? Now I have said, so in this point you have to remember where the maximum pressure occurs. This is the point, point 2. Point 2 where the maximum pressure occurs. And can you tell me that where do we got a question steam table? No, absolutely no. There is no. You will not. There will be no questions relevant to steam table. Okay, so you can freely. You can stop worrying about that. Okay, and if such kind of data like gas table you need or other relevant things you need, so all the datas will be provided. Okay, or necessary datas will be provided in that, so you don't have to worry about it. Right, now moving forward, like again, you have to remember the graphical representations, and how this where the temperature fluctuations will be there, how the temperature pressure graph for each and every component. Definitely you have to remember those things, can't skip. So all will be asking based on the concepts, right? You have to keep your mind open. You have to keep it open. Like any sort of types can be asked. And where we have the maximum temperature is the point 3. We have the maximum temperature. They have asked one time like where they have the maximum pressure. Another time they have asked which is the process of this compressor. So all those things I have already discussed. So process of combustion is a isentropic process where the pressure remains constant and ideal case. Right. Now, there are some very important and very easy tricks. Now, I'm going to tell you how easily you can remember, and without much effort, you can remember the efficiency of the important components. Important components, talking about diffuser, talking about compressor, talking about turbine, and the nozzle. Okay, I will tell you the formula for combustion also, but they have an this four have an very unique connections. Okay, very unique connection. So I will discuss that with you guys. So which will make you to remember. So you have to basically, I hope these points are clear to all. Now I will moving forward to your this efficiency part. Now here I am going to discuss four efficiencies, how they're interconnected with each other and how easily you can remember also. Efficiency, efficiency. Diffuser, we have compressor, efficiency, we have turbine, efficiency, we have the nozzle. Definitely, this efficiency part will cover your compressor, turbine, diffuser, and other parts also. Okay, you can use the same actually. You can use the same thing, but the small concept you have to remember. That's all, and you will remember this if you practice a bit. By understanding lifelong, you will remember this concept and will never forget in your life, right? And all right. So this is a four efficiency we are going to discuss. Now they have a unique relation. So all the relations are going to relate with your change in temperature, right? Change in temperature. So if I say what is a change between this, so it's a bit changing the temperature from T naught 1 to T naught A, right? Here, what is a change in the compressor? T naught 1 to T naught 2, like vice versa. And what is a change between the turbine? Okay, T naught 3 to T naught 4, and within the nozzle T naught 4 to T naught 5. This is a change going to happen between the temperature. Now they have the efficiency says that definitely some ideal to actual, right? It's with some ideal I to actual. So efficiency of actual change in temperature to the ideal change in temperature. Sometimes the ideal change in temperature is also known as a isentropic change, where we will note the temperature in terms of some dash or some prime. Right now, here you just watch it carefully. Let's consider the diffuser efficiency denoted by eta d. Okay, compressor as eta c, this one turbine as T, and this one is nozzle as N. What is that? Change in temperature of an isentropic condition and change in temperature of an actual condition. Okay, so just remember as this I by A. Same for the compressor, change of temperature within this isentropic or ideal condition and change within the actual. And rest, these two turbines are the change in temperature with the actual one with the ideal, actual by ideal. I hope it is quite easy to remember. The first half, the first half of the efficiency you are going to relate, we are going to relate with the I by A and the rest with the A by I. Now you can easily frame it. You can easily frame it by yourself. How? Now, as I said, change in temperature ideal. So, which is the highest one? T naught 1 is going to highest one. T naught 1 by T naught A, T naught 1 by T naught A. Just right. And if I said ideal means, so obviously I'm going to use prime over here. Okay, ideal means I have said here prime, right? Prime. So T naught 1 dash minus TA by T naught 1 by TA, because TA is not going to change. It's a ambient temperature which is coming or entering inside, right? It is not going to change. Fine. Similarly, what we are going to write here, eta C, it's starting from T naught 1 to T naught 2. So T naught 2 is the highest. I will write first T naught 2 minus T naught 1, T naught 2 minus T naught 1. So here the ideal one. So obviously it's starting from this point to this point, right? The end condition will have the prime. So this is the end condition T naught 2 minus T naught 1, T naught 2 minus T naught 1. Clear? Now similarly, we will write this for this as well. Okay. So this is the highest one, as this is the point 3 is the highest one. So we'll write it first. Okay. So T naught 3 minus T naught 4 by T naught 3 minus T naught 4. So which one is ideal? In the denominator term we have the ideal. Here we will put prime. Similarly, here we have the relation between T naught 4 and T naught 5. So as compared with the 5, T naught 4 is the maximum temperature. So T naught 4 minus T naught 5, T naught 4 minus T naught 5 prime. I hope this equation looks very simple to understand, right? If they have given you, provided you the temperature value, you can simply remember this tricks and you can utilize this for rest of your problem. Now this is a common formula to all, right? It's easy. Let me know in the chat box. A defines actual. Okay, kindly excuse me for my handwriting. I hope uh, this kind of tricks will be helping you. Like I hope you will not forget in your lifelong. Like how I have explained this thing. The end points are going to be prime, right? And A by A for the turbine and nozzle. That is actual change in temperature to the ideal change in temperature. And for diffuser and compressor, it's ideal by actual. Repeat the last one is like, see, let me write it here itself. Okay. So here what I'm doing, nozzle, right? What I said for this side, this one we have the actual change in temperature by the ideal change in temperature, right? There may be confusion that which one to give prime, right, when you are making it. So when you're making for the turbine, just make the difference T naught 3 minus T naught 4 by T naught 3 minus T naught 4. Right? Now, where we have the ideal, we have to make the hyphen. Right? So this is the ideal one. This is the ideal because A by I. So this the end means when the flow is coming from 3 to 4, right? 3 to 4. The end one you have to give prime always. End one. Just similarly for the nozzle eta T, how you can write T naught 4 minus T naught 5, T naught 4 minus T naught 5. Right? The end one, this is the A and this is the I. I means ideal. The end, the flow is coming from 4 to 5. End is T naught 5. So this one. So you might have a confusion key whether you have to put prime for T naught 4 or T naught 5. To avoid that confusion, I'm telling you. Similarly, for diffuser, it's I by A. So eta D equals to its starting maximum is T naught 1 minus T naught A, T naught 1 minus T naught A, which is the end one. Flow is moving from A to T naught 1, right? It's moving from TA to T naught 1. End is T naught 1. Where we have ideal, the top. So here we have the top. Here we have the prime. I hope I made you clear. The rest things will be done accordingly. Okay. Now this is the basic thing. Now further, how you can expand in other formations. So other to expand them in other formation, this is a common thing to remember, is an isentropic relation. You have to use this relation for rest of the four equations. And what is a relation? You have to use the isentropic relation for all. So if I see, let's now first solve the diffuser efficiency first. So What is isentropic? That means it's a relation between A and T naught 1. So let's write T naught 1 by TA equals to P naught 1 by PA power gamma minus 1 by gamma, right? Gamma minus 1 by gamma. Now I have seen that it's been like many students but we've been messaging that ma'am, how to remember such formula, is there any tricks like that? So basically there is no tricks, you have to remember it. What I follow from my point of view, right? I know the gamma value is 1.4, right? And zero point 0.4, if I use gamma minus 1 is zero point 0.4 by 1.4. If you use a calculator, if you use the calculator, it will be coming around 1.4. It's like 0.286, right? So I remember, however the combination is P naught by PA, if gamma value is that, it's going to come 286. I don't remember gamma minus 1 by gamma. It's kind of confusing. Several equations are there. So I remember this way with the power, okay, with the number I remember. So if it is like vice versa, it will come 3.5. So I will know that whether I'm in the right track or not. So you can also follow the same tactics, right? So here is gamma minus 1 by gamma. So I can rearrange this previous equation. ये जो equation है, here we have some equations like eta d equals to t naught 1 minus ta by t naught 1 by ta, right? I can, sorry, here we have missed this prime because it's isentropic relation, that is ideal equation. So I can take a common of ta of that, ta equals to t naught 1 by ta minus 1, I will get by t naught 1 minus ta. So now I can substitute this part, right? This, and apply this value over here. I can substitute that. So I can write that Ta equals to P naught 1 by Pa gamma minus 1 by gamma minus of 1 by T naught 1 minus Ta, right? We can also write. Now, recalling, sometimes they are some relation with the Mach number. So you have to also recall T naught 1 by Ta equals to 1 plus of gamma minus 1 by 2 m square. So you can make use of that over here as well. What you can do, so take T naught 1 common again by Ta minus of, you can take common, right? Ta 1, this Ta will get cancelled off. This value, this value is substitute over here, right? If you substitute, you will get P naught 1 by Pa gamma minus 1 by gamma minus of 1. Then here this, if you substitute, you will get gamma minus 1 by 2 m square. So by remembering few of the equations, you can easily solve the rest of the thing. You can solve the rest of the thing. It is going to be much easier. It's going to be much easier, right? So just let me know, is it easy to remember it? I hope you don't have to remember a huge sort of things. If you remember this simple four expressions, that will serve the purpose of your rest of the solution, because you're going to use the same thing. Even you're, they have asked about the compressor problem, you're going to use the same formula. Just kindly give me the feedback so I will know, in future I can make some necessary changes on it, right? Now, without wasting time, let's move to the next, compressor efficiency. So this is a final one for the diffuser. You can remember this equation, this equation. Another is, you can also remember or make use of this equation as well. Any one of the equation you can remember it, right? Now, uh, right. Thank you, Vardhan. Is it all right? Let's moving further to this compressor efficiency. Now, one thing you have to remember in compressor, we use a compression or compressor ratio. We use compressor ratio. So, let me take this ink. So, as it's a phase from 1 to 2, that is point 1 to 2. So, let's recall compressor ratio is P naught 2 by P naught 1. And simultaneously, if I have to include or indulge this isentropic relation over here, how will I indulge? T naught 2 prime by T naught 1 equals to again the same thing, P naught 2 by P naught 1. Then obviously gamma minus 1 by gamma. I hope I have said you the tricks so it will be easy for you. Now again we are going to do the same thing. What is the same thing? Eta c equals to, we will take it common. Which is the common part we will take? T naught 1 we will take it common. So T naught 2 prime by T naught 1 minus of 1 by T naught 2 minus T naught 1. Now this term, right, in place of this, we will apply this one. And we will get T naught 1 P naught 2 by P naught 1 gamma minus 1 by gamma minus of 1 T naught 2 minus T naught 1. And as I've said here, RC, what is a RC? That is a compression ratio. We can also write that T naught 1 equals to RC power gamma minus 1 by gamma and minus 1. And there are n number of problems using this formula. N number of problems, whether you do especially for compressor problems, especially you do for gas turbine problem, whatever it is, you need to make use of this particular problem, right? So this is the final conclusion of it. So based on the given data, you can interchange and find out the result. Just like that, you have to obtain for this turbine efficiency and the nozzle. The only relation which we are using here, isentropic relation. Again, for a turbine, we will use an isentropic relation. We are going to use this isentropic relation. But what is the ratio going to be here? I'm going to use here T naught 4 by T naught 3. Sorry, here T naught 3 equals to P naught 4 by P naught 3 is gamma minus 1 by gamma. I'm just going to take one of the parameter common outside over here, right? So eta T equals to T naught 3 minus T naught 4, T naught 3 1 minus of T naught 4 prime by T naught 3. I'm just going to substitute that right here. So I'm going to write eta t equals to T naught 3 minus T naught 4, naught 3, 1 minus of P naught 4 by P naught 3, gamma minus 1 by gamma, right? So if the P naught 3 4 by P naught 3 value is given, well and good. If not, if they have given the turbine pressure ratio or the expansion pressure ratio, which is P naught 3 by P naught 4, which is denoted by RT, substitute that value over here and you will get the result. Okay, if you compile that, you will get it something like this, that equals to, you will get like T naught 3 minus T naught 4, T naught 3, 1 minus of RT, 1 by RT, gamma minus 1 by gamma. You will get like this. Alright. So similarly, this again, the same procedure has to be done. And this is the ultimate formula. So if you remember this formula, if you know the isentropic process, you can resolve it to the end. Okay, because why I'm showing you, because sometimes there are some questions we need to implement these principles within this process. Okay, and this is all the basic thermodynamics that you are implementing while resolving this formula. Right. So let me do this thing as well, or you can do it without lack of time. I'm just writing the final expression. T naught 4 minus T naught 5. You can also write like eta n into T naught 4, 1 minus of P naught. I hope it's visible. Okay. So P naught 5 by P naught 4 gamma minus 1 by gamma. Okay. So this is going to be the final expressions. Okay. And mm, yeah. And sometimes they ask one more thing. You must know that as well. Like isentropic efficiency with polytropic efficiency. It's again a quite a common topic. It's a, again I'm telling you quite a common topic and very simple formula. Do remember this. So this is for compressor. For eta for compressor means it's for isentropic process, isentropic efficiency. So RC power gamma minus 1 by gamma minus of 1. Okay, RC gamma minus 1 by gamma into eta P. Okay, eta P means here is a polytropic process. It's in the denominator minus of 1. So if there are some relations like they have given some isentropic efficiency and polytropic efficiency together, they have given you some value. And RC means already have said what is the meaning of RC. It's a compressor ratio, right? Gamma is adiabatic is given, right? The substitute 1.4. Okay, so you can use this formula and see which component they have given. It's for compressor. Okay, this is for compressor. Similarly, we have one formula for turbine. Same relation between the isentropic and polytropic. So this is for turbine 1 minus of 1 by this pressure ratio, turbine pressure ratio, gamma minus 1 into eta P, okay, by eta, sorry, by by gamma by 1 minus of 1 by RT gamma minus 1 by gamma. All right. So this is another and eta. It's eta, not n. It's to define efficiency. It's not n, dear. It's efficiency eta. Okay, whatever you say, just consider as an efficiency. It's efficiency between this isentropic process and the polytropic process. Isentropic process with the polytropic process, right? This is one of the important problem. Now we have left over with our compressor the combustion efficiency. Okay, okay, just a second. Now we will continue with our combustion efficiency. Okay, combustion efficiency. So you must need to remember the combustion efficiency, or sometimes it is called as a burner efficiency, right? Combustion efficiency or burner efficiency, right? So as in the combustion chamber, both the air and the fuel are getting mixed. So we will have this formula into calorific value. So they will give you a calorific value over there. Now further this equation can be rewrite. This H naught 2 is an enthalpy. So can be right if they have given the CPG and CPA separately. So accordingly this formula will also change. If they have not given anything, so keep a simple or common CPG into CPG into T naught 3. Okay, CPG into T naught 3 minus MA into CPA into T naught 2, right? T naught 2 divided by m dot f into calorific value or heating value, something like that they will be given. Okay, and please ensure the CP value mostly they used to give 44 megajoule per kg. So you need to convert the unit for this. Keep in mind. Okay, keep in mind. Now this is a general formula for burner or the combustion efficiency. Now there is another alternative way to understand that what is a total mass flow rate or the gases mg is a m dot a plus m dot f. Okay, this is combination of mass flow rate of air and mass flow rate of the fuel. So they can also write like m dot g by m dot a equals to 1 plus of f. Okay, that is F means it's a mass flow rate of fuel by mass flow rate of air. So sometimes they might give you the F value also. So if they give you the F value, so accordingly you have to frame the equation. Accordingly you have to frame the equation. Now there is another case study. There are some problems they ask, like they ask that the fuel ratio is very small. Okay, the fuel ratio is very small. So then that cases what you're gonna do is you just the mass flow rate of air and fuel is it's almost zero, right? That means they are going to be the same. In that case we can reframe the equation as the condition applied. Okay, condition applied, they are very small. Eta b equals to H naught 3 minus H naught 2 F CV. Okay, when there is very small, right? This also sometimes they repeatedly they have asked the concept from here. So do not skip this formula. Definitely one question will be coming. And if you ask that what is the ratio of air fuel, if they ask relevant, it is almost starting with the 60 is to 1 to 95 is to 1. Okay, air is to fuel ratios for an gas turbine engine globally. This is a globally I'm telling you, right? And if they given for actual and ideal cases of air fuel ratio, then you can also use that fuel air ratio of theoretical by fuel air ratio of an actual into 100%. These are the 5 major formulas that is going to help you out. Then apart from that, jet engine, the performance, how they're working on their environment, different environments. So all those things also you have to practice. All those things are again important. Some theoretical thing like how they're working on the based on the performance, a temperature, pressure, where we'll have the maximum pressure. Then we have some propulsive efficiency, how they're related, thermal efficiency, how they're related. All right. all those things again, those things are again, F means the fuel ratio. Show the entropy for turbine. Okay, I will show that again. I will show that formula. Okay, so prepare that. And so all those things we have cleared. And talking about this your velocity triangle, do not skip the in the velocity triangle. So talking or solving about the velocity triangle for axial compressor, for centrifugal compressor, then we have turbine, right? They have a very unique relations. So you can, I have made a separate video on that, so please do not skip those videos. I will put in the description box as well. So please do watch that. It is going to helpful for you guys, because I have shared some tricks over there as well. Okay, now I hope you have noted down this thing. And now I will share my another screen with you guys. um, I hope my screen is visible. Now I will give you some glitch or ideas about this our rest of the topic. Just before that, I just want to ensure that my screen is visible to all. Just would like to check it. Yeah, it's visible. Right. Now there are some topics. Yes, as you have said about nozzle, this is very very important. Which comes, how can you classify or how can you distinct nozzle for an rocket nozzle, or an we can say, you know, mm, rocket propulsion nozzle and the air breathing nozzle. Why we have the rocket propulsion? Why we have a convergent divergent nozzle for an um, you know for a rocket propulsion or a rocket engine, right? As I have said those things in aerodynamics also, that one is that it helps to provide, better kinetic energy when the Mach number is more than 1, right? And second is, now we have seen, you might have seen that we previously had a conical nozzle, now we have a bell nozzle, gradually converted into dual bell nozzle. What is the reason behind it? Because that shape provides an huge number of expansion shock waves. And what is the property of expansion shock wave? Behind the flow, it helps to increase the decrease the static pressure and helps to increase the velocity or the Mach number, right? So multiple types of expansion shock wave, it leads to increase the exit pressure, that which will help to increase the kinetic energy and leads to increase your what we say that mm, trust, right? Now I will give you the glitch, that what are the things you have to study from the rocket propulsion. And no doubt this is again another very 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 important topic. That we First is to understand the classifications, the types of you're having here is a pressure feed system, pump feed systems. Now here again, like previously I've said, how this parameter, there are so many different engines are there. Ramjet engine, so they might ask that whose specific impulse is going to be more as compared with the other one. The comparisons, you have to study according to the comparisons. So here you can see one simple, I mean say, that table, right? So what we can bring to some certain conclusions from here, that the thrust to weight ratio for a rocket is going to be the most highest as compared with the turbojet ratio. Now talking about the specific fuel consumption is going to be the more, right? It's going to be the highest for the rocket as compared with the turbojet. So as we talk a turbojet, gradually we have other high bypass ratio, low bypass ratio. It's going to be less, right? So again, the specific thrust is also more, but talking about the specific impulse. So specific impulse is more for a turbojet. So such kind of comparative of that performance parameter and the comparison of different engines are expected, are, and it is a very common in a gate exam. So when if you're planning for the last moment, please do prepare likewise. And so how this specific impulse and the formulas are related with one another, right? And here you can see this total impulse, how we can calculate the total impulse, what is a unit, and the specific impulse, how you can calculate, and what are the given parameter, what is mean by exhaust velocity, how you can find out exhaust velocity, mass ratio. Definitely one question will be coming from the mass ratio, the relation with the mass ratio of propellant mass. Okay, propellant mass is a fraction of propellant mass to the initial mass, that is initially, or the total mass you can say. Okay, then we have another important relation is that thrust. How do you calculate thrust, and what are the relations, what is thrust coefficient, what do you mean by thrust coefficient, what are the relations, how you find the chamber pressure, what should be the throat area, what should be the thrust produced by the engine. Okay, then we have characteristic velocity, very important. Do not skip this formula, simple formula. They might ask you in 1 or 2 marks question. Definitely, these never skip this numericals. Okay, these are very much scoring. Thrust, if thrust, there is a quite confusing thing about the thrust coefficient and the characteristic velocity. So relation between the thrust coefficient and the characteristic velocity. Okay, you do study. No need to remember this complicated big formula. Nobody is going to ask you this. They will ask with this small relevant relation. Okay, then here very importantly, they will ask about the propulsive efficiency. There is a difference in propulsive efficiency for an rocket engine and the jet engine. So propulsive efficiency, what is propulsive efficiency? There are different types of I mean thermal rocket propulsion, ion propulsion, nuclear propulsion, chemical propulsion, how their variations with your specific impulse. They are going to focus on the how or which particular the propellant have the maximum specific impulse. They are going to relate the relation. So please do understand that. So this iron or electrostatic propulsive efficiency have the maximum specific impulse as compared with the chemical one. And within the chemical one, again, we have a classifications like liquid, and we have bipropellant, we have a bipropellant, we have a liquid propellant solid, which is having among this, which is having the maximum specific impulse. So bipropellant is having the highest specific impulse. Or if they have the cryogenic, if they use the cryogenic among this, so choose the cryogenic one, right, which is close to 450 seconds. Okay, where solid is around 380 seconds. So, I'm quite sure just focus on the specific impulse and their parameters, how they're connected. Now, there are two conditions: gravity free, drag free equation. Another is with forces acting on the atmosphere. So you need to use some solve some numericals using this formula Tokozewski rocket equation, right? This one, and how they are related with the mass ratio, with the velocity curve. Try to understand these parameters, relate with the mass fractions. Then we have this again formula without zero gravitational force. Without, this is a without zero gravitational force, or considering the constant gravitational acceleration. Moreover, we can say constant gravitational acceleration. So this definitely one problem will be coming from your this gravity free and constant acceleration. So remember this two formula. Next is multi-staging and all. These are the rarest of rarest. Like they might ask you like, what do you mean by payload ratios, structural ratios, how they're related, and how you can obtain the relations, and maybe some application based. These are the rarest question. Okay, these are the rarest question about this from the rocket propulsion, especially from the rocket propulsion. But you can expect something from the multi-stage, like how to calculate the payload, how will you find what should be the total value for the series multi-stage rocket, effective speed and all those things. You can expect this question, right? So these are all then is there. Then apart from that, each and every property, like moving forward to this chemical, we have monopropellant. What are the list of the monopropellants? We have biopropellants. What are the list of biopropellants? Then which is a hydrochloric gel type, and what is the advantages, disadvantages of solid, hybrid and liquid, and what are the important components, important parts and their functions. So just have a outlook on it. They don't ask much, but definitely prepare the propellants, the different types of propellants that they use in it. Okay, so definitely they will ask. So I hope I have covered my best within 1.5 hour. 1.5 hour. So any other questions? um okay, Ankush, I will share some link over here, so you can go and visit to the link and access the certain documents, right? I will do provide to you guys. Any other questions are welcome. And don't forget to give the feedback how you felt about this session. uh, did you felt it useful? Did you learn anything more? Did you learn any new formula in it? I would like to know the feedback. I'll be happy to know. And as I said, do not skip the things which I have said important. Do prepare. And yes, I think that's all from my side. Okay, I would love to take if you have any questions. And it will be a suggestion from my side. Please do check the units. Uh, Definitely, I can say from this topic, uh, 15 marks. If you plan this trust efficiency, then Brighton cycle, then thermodynamics easily. If you prepare all those formulas, how they're connected, if you're quite clear about it, now this topics alone and the formulas, if you thoroughly practice the formulas, definitely you can out of, I'm talking about out of 25, easily you can score 15 out of 25. For an example, they for propulsion they're asking 25 marks, right? So studying this, you can easily score 15 easily. But as I've said, you have to be careful with the units what they have, because the main purpose of the gate is to make you guys confused. So you should not be confused with that. They have to be fixed. All right. Okay. So any other questions are welcome. I hope there is okay. No questions. So thank you everyone, and all the best for your exam. And tomorrow we will have one more session with the flight mechanics. And okay, we'll see you tomorrow then. Please stay tuned to our channel for further notification. So okay then, good night. See you tomorrow.